All right, try that again. Hi, how are you? What's going on? It's another week in Earth and Space Science, and here we are. So today is Nova's explosions in space. Basic nova is any kind of explosion in space. A supernova, hypernova, or nova. Those are all novas. They're all explosions in space. The plural is Novae. You put an E on the end. It's a Greek thing, I guess. And the little ones, which make white dwarfs and planetary nebulas, though, that's just a main sequence star that reaches the red giant stage and then collapses inside of itself. Literally, the insides collapse, but the outside looks perfectly normal. And so the insides collapse, rebound, explode outward. That's a basic nova. I mean, it can happen in a main sequence star, a supergiant, a hypergiant, or when black holes combine or collide. So you've got novae, and literally just big boom in space. And the main sequence stars are going to make your white dwarfs and your planetary nebulas. Then you've got your supernovas or supernovae. That's a little bit more information. There are at least three types. I'm sorry, let me say that right. There's two types and at least three categories in type 1 and at least two categories in type 2. I'm not going to go into every category. I'm not going to talk about every single possible type. I'm going to talk about the most brilliant, the most amazing explosions, and I'm going to talk about, your basic what's supernova. So supernova, a large star can collapse. It's red, it's hypergiant, it's supergiant, its outside looks perfectly normal, the inside collapses, and then that compression makes a big boom, and there's an explosion going out from the center. That's a supernova. That's one type of supernova. There's another type of supernova. I'll get to that. They have either got a lot of hydrogen, that's a type 2, or almost no hydrogen, that's a type 1. But type 1a, there can be some hydrogen involved. That's a different story though. So type 1, less hydrogen, almost no hydrogen, sometimes zero hydrogen. Type 1b, lots of silicon. Type 1c, no silicon. I skipped type 1a on purpose. There was a reason I skipped type 1a supernovae. I want to talk about that one very specifically because it's pretty cool. So type 1, less hydrogen, almost no hydrogen. Silicon, very abundant in a type 1b. Silicon, not abundant in a type 1c. So they categorize it based on, it's all based on the chemistry you see in your absorption spectroscopy analysis. And we've talked about absorption spectroscopy. You don't need to know the word. We've already taken a test on it. Not a big deal there. And so type 1 supernovas, very little hydrogen involved. Type 1a, the ones we can see, the ones that go boom real big, the ones that are so incredibly bright you can see them from galaxies away. Type 1a supernovas work a little differently. It is not a giant star exploding. It is at least two stars involved. I guess there could be more. I don't know. I've never read a circumstance where there were 3 stars involved, but it could happen. It's entirely possible. It could be 4 stars involved if you can find a system with 4 stars. They do exist. So type 1a supernova, I really want you to know this one. Type 1a supernova, a white dwarf. A star has gone through its entire life cycle. It turned into a red giant. It collapsed. It exploded and made a planetary nebula, probably. It's a white dwarf. And somehow it still has a binary partner, a pair of stars orbiting each other. I need to go get some graphic of 2 stars orbiting each other. A binary pair of stars, I want you to know, a binary pair of stars is 2 stars orbiting each other. And if one of them is a white dwarf, it has already exploded. It has novaed, it has exploded. And its partner is losing material to it. The white dwarf is pulling material from the binary partner. It's a star vampire. It is dead. It is a zombie. It is gone. It's done with its fusion, but it's stealing hydrogen and other materials from its binary partner. And that partner is losing mass, and you can see the matter going around little white dwarfs being stolen from. It's like that scene from Star Wars where they're stealing material from the sun and putting it into the big machine to destroy planets with. You can see the matter actually going into the little white dwarf from the other star. And then the white dwarf gains enough mass to not nova. It's not just going to nova. It's going to supernova. So the star died. It novaed. It boom. Planetary nebula. White dwarf in the middle of it. The next star over started losing material. The star, the white dwarf, boom, like a massive, incredibly explosive, you can see it from galaxies away, boom, supernova. Very, very vibrant, very, very explosive. More energy released in one day than galaxies can produce. The brightness is like galaxy bright. It is very, very, very visible, and you can see it from really far away. Really cool stuff. And so type 1a supernova, the biggest booms we can see. It's almost the biggest, I got the word out that time. Almost the biggest explosion in space. Almost the biggest explosion in space. We're going to talk about something later in a minute here that's a little bigger. So type 1a supernovas, big explosion involving two stars, white dwarf and its partner, its friend, its best buddy growing up. They grew up together, and then the one turns into a zombie and eats his friend. It's really quite tragic tale that you might see on TV these days. So then there's another type of supernova. Instead of type 1, it's type 2. Lots of hydrogen involved. It's on the absorption spectroscopy, it says very broad bands of hydrogen, meaning they're very, very fast moving, and there's a lot of it. So type 2, I'm not going to go into type 2a, b, and c. They do exist. There are definitions for things. Let me just remind you, the difference between a, b, and c are going to be chemistry. Chemistry is really the big difference when you're categorizing your supernovas. The explosion is creating all kinds of elements. And when they're making a lot of silica, you got your type 1s. When there's a whole lot of hydrogen still, even though it should have exploded and converted and fused, if there's still a lot of hydrogen, that's type 2. So type 1, silica, type 2, hydrogen. Except for type 1Cs. Well, I already went over all that. So then that's your novas, your supernovas, and your type 1a supernovas. Those are, I want you to know those three. I also want you to know what binary pair is. Then we have the big one, the explosion that can create gamma ray bursts. And we're going to talk about gamma ray bursts completely separately, not in this video. The ones that can make gamma ray bursts are black holes. And when a black hole, it's that a star had to be big massive star dies, it's a red supergiant, it's a red hypergiant, then the outside stays red and sun-like, the inside collapses. Boom, blows itself up. Supernova. The black hole created at the center starts pulling in all the material around it and getting bigger. Well, not bigger and bigger, really, because the black hole is this big. A black hole is called a singularity, but we're going to do black holes for an entire video. Just on black holes, we got an entire video. And so this tiny speck is absorbing more and more material, and the black hole can explode again. You can get a black hole meeting a black hole. If two galaxies combine, I showed you galaxies combining and colliding and how the stars get rearranged, but there's not a whole lot of actual stars smacking into each other. But if you get the core of a galaxy, a supermassive black hole, and the core of another galaxy, a supermassive black hole, and those two get close enough to get, there's just, oh, boom! It's called a hypernova, and it is the brightest, well, I can't say brightest, I apologize. The most energetic release of energy called a gamma ray burst that you can get. It isn't as visible. It's not a whole, there's visible light, there's a big explosion. It's not as visible as it is radiation. That's just gamma rays, boom, radiation, almost the highest frequency energy, gamma rays in the universe. The only thing more high frequency than a gamma ray is a cosmic ray. And where's the line between a gamma ray and a cosmic ray? I don't know. Ask Bruce Banner. I don't know where there's the division line. I don't know if it's a yoctometer, if it's smaller than a yoctometer. I don't know. I have no idea where they draw the line between gamma rays and cosmic rays. I can go look it up, but so could you. So hypernova, I forgot the word again. A hypernova, a big, massive release of radiation called gamma ray burst. So a black hole eats another black hole, and it doesn't have to be a supermassive black hole and a supermassive black hole. It could be a massive black hole and a normal black hole. It could be a normal black hole and a normal black hole. And we're going to talk about different types of black holes later. There's normal and there's really big. Like I said, there's stars, there's normal and there's really big. Black holes, there's normal and there's really big. There's not going to be a medium. So you won't have a medium black hole eating a small one or a medium black hole being eaten by a bigger one. No, it's two big ones hitting, a big one and a little one hitting, or two little ones hitting. That's it. That's where your hypernovas come from. So that's your kind of basic hypernova, nova, supernova little lecture right there. And I'll see if I can get some good images. I can definitely find some good supernova imagery for your type 1a supernovas, because they are very visible and you can see them through telescopes from far away. So let's draw a line at there. All right, we're going to stop, and then next video, star zombies, the dead stars, the ones that we want to talk about, the black holes, the neutron stars, the white dwarfs, black dwarfs. Those are going to be next time.